The broadcast is now starting. All attendees are in listen-only mode.
Welcome everyone to Fused Silica Selection, Solutions for Price versus Performance, a webinar presented by Heraeus and hosted by Photonics Media. My name is Robin Riley and I'm the Photonics Media web editor. Our speaker today is Dr. Todd D. Jaeger, Global Sales Director of Commercial Optics for Heraeus Quarzglas. Todd will be speaking today on fused silica properties and applications and how to select the variety that best meets your needs. A PDF of Todd's presentation will be emailed to all registrants after the webinar. If you have any technical issues during the webinar, please log out and log back in to rejoin. A recording of the webinar will be available on the Photonics Media website shortly after the presentation. We encourage you to ask questions throughout Todd's presentation. Just type your question in the question box, and Todd, along with Dr. Frank Nurnberg, Global Sales Manager for Heraeus Quarzglas, will answer as many as possible at the end of the session. Before we begin, we would like to ask attendees a brief poll question. And the question that we would like to ask is, for which markets or applications do you use fused silica? And the possible answers are laser, metrology, medical, science and research, astronomy, or aerospace, or others. I'll give everyone a few more seconds to respond. And now I'm going to close and share the responses with you. And those are your responses to poll question number 1. And now I would like to turn the presentation over to our speaker, Dr. Todd Jaeger.
Thank you for the introduction, Robin, and thank you to all that have joined us for our webinar today. The top question that we receive at Heraeus is, with all of the different types and grades of fused silica, how do I know what's appropriate for my application? How do I spec things properly? Make sure that I'm not over or under speccing. So this is why we've put this webinar together today for fused silica selection, solutions for price versus performance. The agenda for today is split into 5 sections. First, we will do an introductory portion where I'll introduce myself, the company, and a bit about the history of fused silica. Next, I will highlight the problems that need to be solved, what current solutions are utilized, and what the consequences are of these solutions as they're implemented. After that, we will delve into what makes a material quartz or fused silica by examining physical properties, optical properties, and the manufacturing process. For the 4th section, we'll examine applications and their challenges. We will also propose solutions for which materials fit best for these applications. Although there are a myriad of applications, we will concentrate on the near-infrared, the deep UV and UV, and 3-dimensional optics. Finally, we will guide you on what to specify and provide you with a selection tool to decipher which fused silica is best for your application. So without further ado, we'll kick the webinar off. My name is Dr. Todd D. Jaeger. I'm with Heraeus Quarzglas. I'm the Global Sales Director for the Commercial Optics Division. I've been in the optics and photonics industry for over 15 years now. By training, I'm actually a physical chemist who specialized in lasers and spectroscopy. My postdoctoral work was completed at Washington University in St. Louis on velocity map imaging in the Loomis group. After that, I went on to NASA and joined their laser risk reduction program at Goddard Space Flight Center. Currently, I'm located in Beaufort, Georgia at the Heraeus Quartz North America facility. So who is Heraeus? Heraeus was established in 1866 and is today one of the largest family-owned companies in Europe. Heraeus is comprised of several business units. We have over 12,000 employees at more than 100 sites in 38 countries. Although the largest portion of our 21.5 billion euro revenue in 2016 came from precious metal trading, we still have a high focus on innovation and high value solutions. In 2016, our product revenue topped 2 billion euros. Heraeus Quarzglas is a significant contributor to this product revenue. So let's look at a bit of the history of fused silica and quartz. Heraeus quartz business really began in 1899 when Dr. Cook developed a process for melting quartz. This resulted in a patent in 1905. 7 years later, Heraeus Quarzglas was founded. The key developments for optics in the quartz and fused silica world really began in the 1950s with the production of the first quartz optical glass. This was followed on by a production process for synthetic fused silica to create a material with much lower metallic impurities. In 1980, we specialized in a new process to create a material with very low infrared absorption. As far as the applications go, we've listed just a few of the key ones we're involved with. This by no means is a complete list of what Heraeus has done over the years. But as you can see from the 1960s on, from retroreflectors on the moon for the Apollo 11 mission to significant contributions in microlithography and enabling technologies for astronomy, nuclear and scientific and research programs, Heraeus has provided high quality optical materials for half of a century now. And we will continue to develop new materials and contribute to cutting edge applications as we move forward. We'll move forward from there now that we've talked a bit about the history and get into the meat of the issues at hand. As mentioned, there is a dilemma as far as having many grades to choose from and having to work on bringing our price down but still keeping our performance up. Status quo, just to review that, we don't want to fix it if it isn't broken. We rely on third-party opinions, so-called phoning a friend. We Google ourselves into confusion, and we often don't question the drawing. If the drawing states a fused silica type and then says or equivalent, it's rare that we go after and find out what the equivalent would be for fear of the unknown. Additionally, we find application notes online that specify one material or another that we believe fits with what we're doing, but we're not quite clear on. So the consequence from that can be nearly devastating. Any of these issues that you see here really would come from over or under specifying. If you over specify, of course, the material is going to work perfectly, but you might be paying for more than what you actually need. And if you under specify, of course, the performance can and will suffer. So let's delve into what makes up fused silica. First, we'll touch on the physical properties. These can be found on our spec sheets and on our material catalog. We'll touch on each of these. First, we have our thermal properties, such as the coefficient of thermal expansion and the working temperature. This becomes important in an application, say, where you are looking for windows for a high temperature furnace. Your standard optical glasses out there would melt at extremely high temperatures that fused silica can withstand. The chemical resistivity against acids and other items becomes important in a marine setting, for instance, where there's salt water, or in highly caustic environments. If you're looking at something electrical, fused silica makes an excellent insulator. It actually retains high resistivity at elevated temperatures. And of course, for mechanical, you really want to consider what you're putting the material and the optic through. What stress is being put on the system? Can the hardness and strength of the material put up with what you're doing to it? And then finally, in many applications, you really need to consider the radiation hardness. How does the optic degrade over time when exposed to various types of irradiation? Does it solarize? Are there color centers formed, etc.? What we really want to concentrate on today more is on the optical properties. So we'll go through each of these individually with the topics that were mentioned earlier. We'll look at the infrared and UV transmission. Really, the transmission would be defined as how much light makes it through the material and how do impurities in the material influence this value. Below that, we have absorption. How does OH content affect the absorption of the infrared, for instance? What can be done in the UV to prevent solarization or darkening of the material? We'll look at the bubbles and inclusions. This can be important in both laser applications or in imaging. In laser applications, these become sites for damage or for scatter. Fluorescence, this can occur from impurities within the material. It can be detrimental in a sensitive spectroscopic application, for instance. We'll delve pretty deeply into homogeneity of the refractive index and how this variation in different directions affects the performance of an optic. What is a 2D material and what is a true three-dimensional material for three-dimensional optics. And then we'll touch briefly on a few of the other optical properties, birefringence, residual strain, stress, stria, refractive index. All of these are items that can be found on the material spec sheet. So as we all know, it's not limited to one fused silica. There's not one Band-Aid or one item that we can select that's going to satisfy needs across the entire light spectrum. There are optimized grades for the various applications. The properties of quartz and fused silica are determined in the manufacturing process. We're going to cover the steps from the production of the material all the way through to its final measurements. We split it into the 5 main categories here. It's really fusion, which is the creation of the material, homogenization, which we'll go through a little bit about our proprietary process and how that works to yield a superior material. We'll talk briefly about forming and annealing, machining, and then end up with metrology, because if we can't measure it, we can't make it. So fusion is how the material is made. The production method that's used really determines the properties of the end product. We will refer to the end product as either a natural fused quartz, which is on the left side here, or a high purity fused silica, which is on the right side here. The fused quartz begins as a crystalline grain as the precursor. Although we can produce this either in electrical furnace and crucible, as you see on the far left, or we can do this with a direct flame fusion, the physics are very similar. The grain is heated to a temperature, a very high temperature, where the crystalline structure actually breaks down. The grains then fuse into an amorphous silica material, and at this point, the material would be a fused quartz. The downside for this process is that any impurities that you would have in your raw material and your crystalline grain are going to be baked into the final product, so to say. So metallic impurities, for instance, can be an issue with this formation technology. In order to produce a material that is high purity and has much, much lower impurities, we would go with a flame hydrolysis technique. There are 2 techniques that we utilize. One is OVD, or outside vapor deposition, and the other is direct quartz. Instead of using a solid precursor, we use a silicon-containing gas. This gas then is burned within one of these flames in a hydrogen and oxygen environment. In the OVD process, we have a tube or a target that's rotating, and we build up a soot, which is really a silicon dioxide, but it's a lower density than what the final fused silica would be. This soot body, as we refer to it, is then taken through another process at very high temperature, where the vitrification and the formation of fused silica actually occurs. Alternatively, direct quartz is just what it states, and this is where we would still have a silicon-containing chemical compound that goes through the flame hydrolysis, but this hits a target, and the target is moved away slowly, which allows you to build up layers of fused silica. The next step for either your quartz or your fused silica is one that's really unique to Heraeus material, and this is the homogenization. The goal of this step is to remove variances in the refractive index. On the right side, we see an example of a material that we would say is as produced, without any additional homogenization. And so you can see that there's a gradient of the refractive index within this interferogram that we're looking at. It doesn't mean that this is a bad material. It certainly has uses for a non-homogenized material. For instance, a very thin debris shield for laser machining. This is an excellent material for that in order to bring costs down, or for a mirror substrate. But if you're looking to make a window or a lens or a prism, an A-sphere, etc., for a higher end application, you really need to look at a homogenized material. So we correct for any of these inhomogeneities through this proprietary process, which is really a mixing process. Without getting into too great a detail, the material is heated up again and utilized in our special machines where the glass is actually mixed with itself. So if we mix it one time, for instance, we would get what we call a 2D homogenization. So this means that it's homogenized in the functional direction. So if we were looking at this interferogram and it was a window, this would be the direction that the light passes through. And this would be the direction on the side, so orthogonal to the functional direction. The best analogy for this is to consider a stack of business cards, where if you look down on the stack of business cards, you can see that the name and all the information on there, and every card underneath that is unique. It's homogenized in that direction. But if you look from the side, you can see the edges of the business cards. So these edges or steps that you're seeing here come from the stacking up of the fused silica layers during the deposition process. If we run the homogenization again in the opposite direction, we can homogenize in that other area that was not homogenized for 2D. And this gives you a material that's excellent for making prisms, retroreflectors, etc. for 3D optics. The forming and annealing is a vital step. We can take the ingot that we form in the earlier processes that were mentioned and place a certain mass, calculated mass, within a carbon mold. The carbon mold then would go into the large forming furnace, be heated back up, and this would go through a reflow where we can make rectangular or round various sizes of ingot. That material then would go through an annealing process. You can think of annealing like a controlled cooling process where it's put in hot into a hot oven, and there's a grade of the temperature being brought down over time. The purpose of the annealing is to help remove any residual stress and strain that's in the material. From here, we can take it through to machining, and this is really your standard glass machining. So you can use a 3-axis or 5-axis machine. We can do this in-house, where we can turn it into a cut blank, a precision cut blank. We can do sawing to make it into plates, core drilling for rods, grinding, lapping, polishing, etc. And then, of course, we have the measurement steps. And the pictures you see here, one is our environmentally controlled automated system for measuring the homogeneity of the material. This is located in Hanau. And then on the right is a machine that's measuring the stress induced by refringence. But the metrology would also cover looking at the bubble grade, the OH content, etc. And these items then that are measured would go on to our spec sheet. So as you can see from this section, the difference in the various grades really comes from both the fusion and the post-fusion processes. Each of these specs can be found on the top of our table in the material catalog or spec sheet. And if you're looking for a material that is outside of one of these specs, just send us an inquiry. We might be able to help you out there. So now that we've seen a bit about the material, we need to think about the applications. As each application has its own unique challenges, we need to understand what is it that we need to pay attention to. Now, as mentioned previously, there's a multitude of applications for fused silica. Today, we're strictly going to focus on 3 of these, and that's for the near infrared, the deep UV, and the UV optics. And finally, we'll go into the 3-dimensional components. But at this time, we're going to pause briefly to put up another poll question.
Hi, Todd, and I will launch the second poll question here. Okay, and the second poll question is, what is your primary wavelength in the NIR/IR? And the possible responses are 800 to 139 nanometers, 1040 to 1079 nanometers, 1080 to 2000 nanometers, greater than 2000 nanometers, no application in this wavelength region. I'll give you a couple more seconds. And I'm going to close this poll, share this poll, and those are everyone's responses. Thank you. And now I will hide the poll, and it will be back to Todd. And Todd, we should be back to you, are we? No. Todd, I am going to make myself the presenter, and then I'm going to turn the presentation right back to you. I apologize for this.
No problem. Okay, I think we're back on the air here. And if we aren't, certainly let me know. So let's dig into some of the applications here. First, we'll start with the near-infrared optics. Now, for this, we chose three different areas within, three different applications within near-infrared optics. So this would be laser material processing, high-energy laser systems, and research lasers. For laser material processing, this is really used for your laser welding, drilling, cutting, etc., for the automotive and flat glass industries. The challenges are you're putting a lot of light through these optics, which if there's absorption can cause some heating. So we want to make sure that the optics and the focal point is going to be stable under a thermal load so that we understand the depth that we're machining at. We also need high throughput for these production processes. And to protect the more expensive optics within the optical train, we'd want to look at a low-cost debris shield. Now, for the high-energy lasers and research lasers, whether you're talking about a fusion laser system, directed energy systems, or something in astrophysics or the gravity wave observatories, the challenges really end up being the same. You need the best possible performance because these are very, very difficult programs. These are cutting-edge experiments. Things are being done that have never been done before. Of course, wavefront conservation is very important. If you think about the laser fusion facilities, you're focusing nearly 200 beams onto a spot that's about the size of a pinhead. And of course, if you have any variation in your wavefront, your focus isn't going to be where you need it to be. They need very large optics, and they need these optics in high quantity. And of course, lowest absorption, bubble and inclusion free so that we don't have damage from that, low bulk scatter, and very high laser damage threshold of the material itself. So what are some of the specs that we should look at? Well, the infrared transmission, absorption, and the bubbles and inclusions are three of the important areas to consider. When you're looking at the infrared transmission, you want to consider what wavelength are you operating at. If we look at the transmission spectra of several of our different materials, we can see that some really have a lot of absorption in this band here. These are materials that are higher in OH, and in the infrared, the OH is actually going to absorb. We show that over here in the absorption. We have in the blue a fused silica that has a low OH content, and in the orange is a fused silica with a high OH content. These are absorption bands from the OH itself, and then we've overlaid a few of the common laser wavelengths. So you can see that on any of these wavelengths, even at 1064, there is some absorption, and in some cases significant absorption on these laser wavelengths. What happens with that is that you get attenuation of the beam. This heats up the optic. You get a localized change in your refractive index or a heating of the entire optic, and your focal point will shift. So you're not machining it where you'd like to be, or you have a distorted wavefront. Additionally, if you have bubbles and inclusions, the high power laser can go through internal lensing. The bubbles and inclusions themselves are sites for damage mitigation. And unfortunately, as you can see from the picture here, once the damage starts, it doesn't get better. It gets significantly worse with each laser shot. Now at Heraeus, we spec a bubble class 0 as a material that doesn't have any bubbles larger than 80 microns in it. We also have a special bubble class that's available with no bubbles in it larger than 10 microns, which is available on special request. So what have we learned for this? Sorry, there's an animation and it's not starting. There we go. So for the best performance in the near infrared, you want to go away from a natural fused quartz towards a synthetic fused silica. This is going to give you lower metallic impurities, which can cause absorption. You want to go, instead of a high OH material, you'd like to choose a low OH material, which will give you lower infrared absorption. We show in this graph down here several of our material types. The supercils are our synthetic fused silica, and the infrasil is actually a fused quartz. And we have a logarithmic scale, and you can see that even at 1064, that the absorption really scales with the OH concentration or with the metallic impurities. So in a very, very high-end situation with a high power laser, your supercil 3001 or one in that family would be the best material to choose because the OH content is less than 1 part per million. Always consider the bubbles and inclusions and how those are going to affect the performance in your system, and consider how much does the absorption matter. So you consider your laser parameters versus acceptable absorption versus price. If you're looking at our spec sheet, you want to look for dark blue, which is going to be your synthetic fused silica. And then we have a column that would be OH content, and it's in parts per million. And so you want to choose something that's on the lower end, and these are our lower OH materials, anywhere from 300 ppm down to less than 1. And I believe at this point, actually, we're going to pause for another poll question.
Okay, I am trying to open the poll question, and I'm having a little bit of an issue with that, Todd. So let me keep working on it. You keep going, and I'll let you know when I have it open.
Okay, no problem. We can do that. So let's move to the opposite end of the spectrum, so to say, where we go from the longer wavelength to shorter wavelength. This would be for our deep UV and UV optics. There are a few applications out there. For this, we really looked at lithography, medical use, and then the general kind of catch-all of research and commercial. Within your lithography, excimer lasers are going to be the light source of choice, either your krypton fluoride at 248 or argon fluoride at 193. And of course, this lithography is for your semiconductor integrated circuits and chips. As far as medical goes, you have LASIK, where you're using the excimer laser to ablate in a controlled way part of the cornea. There's also angioplasty, where the laser is used to ablate blockages within arteries. And then dermatological conditions, where the laser is used to treat some issue that someone is having with their skin, for instance. In research and commercial, there's a lot of spectroscopy out there, including laser-induced breakdown spectroscopy, where UV lasers are used, laser marking of materials, and then of course in nuclear reactors and nuclear tests, the Cherenkov light guides. The challenges for all three are very similar. You need to worry about the radiation hardness. How is the UV light going to affect the material? How's it going to degrade over time? Typically, you want a long lifetime. You need a high homogeneity to have a good tight focal spot. You want that focus to be stable. Scatter is never good because you're talking about UV photons, which can cause damage to the eyes and other items. You want reliable performance, especially when you're either making millions of integrated circuits or if someone's machining your eyeball. And you want this to be reproducible with limited downtime. Now, if we look at some of the specs here, once again, the transmission and absorption are important, just as they were with the infrared. And then there's a third item called compaction that I'll briefly cover. For the UV transmission, you really want to consider what wavelength you're operating at. If you're at 193, you can see that infrasil is probably not going to be the material of choice. The absorption bands that you're seeing in the infrasil are really due to metallic impurities in the fused quartz process. So you want to avoid that. Now, when we talk about absorption, when we looked at infrared, we were really considering not only some absorption by the metallic impurities, but primarily the absorption due to the OH content. In the UV, we're more concerned about not single photon absorption, but a 2-photon absorption process that can occur. With either your krypton fluoride or argon fluoride, if you have a 2-photon absorption phenomenon or event that occurs, you've got enough energy within the system to break the silicon oxide bond. When this happens, you can form color centers within the material, and this is when your solarization can occur. It also can cause defects that then would have fluorescence. If you have some free hydrogen within the material, this actually will saturate these open bonds and give you sort of a self-healing material. Now, compaction is really a special case. It really only happens under certain laser parameters, but it's a molecular compaction of the actual SiO bond. This causes a localized change in the refractive index, which can induce birefringence. If it's a topic you're interested in, please contact us and we can provide some additional information. So what's the solution then? You want to go for an ultra pure synthetic fused silica. The elemental impurities, individual elemental impurities in our ultra pure synthetic fused silica are typically less than 10 parts per billion. You want to think about the defect centers and absorption at the applications. Is your laser fluence very high? In that case, you're really going to want to use a material that is not going to damage in this way. Hydrogen repair is an option. These are special materials that are hydrogen doped that we can make on request. So you have to consider the operational time versus the lifetime you're looking for and the cost of ownership for the system. One thing to note is that the high OH materials tend to be more stable against damage for UV radiation. So if we go to the Heraeus spec sheet, once again, we're going to look for the dark blue boxes. And within the dark blue boxes, we're going to look at the OH column and consider ones that are higher in OH content. So the best ones are obviously going to be these ones that are greater than 1300, but certainly for some applications, the Supercell 311 and 312 work extremely well. So we'll move now from the wavelength spectrum and begin to talk about the 3D optical components. Now, what we mean by a 3D optical component, obviously a prism and a retroreflector, that's obvious. That's, let's say, in a right angle prism, that you're moving the light within a few directions, so the refractive index needs to be consistent through that entire light path. Same with a retroreflector. For a lens or an A-sphere, it's not really as obvious why a 3D material could be superior. But if you start to think about something that has a very steep radius of curvature, for instance, in order to avoid any astigmatism, coma, or other aberrations out at the edges, you really need to have a 3D material to make this optic. So the challenges are the same for any of these, and it really boils down to having a multi-directional optical isotropy within your material. Now, what should be noticed is that the Heraeus proprietary homogenization process is the only one that yields a true three-dimensional material. Other processes that claim a 3D material really don't satisfy the requirements for being what we would consider a true three-dimensional material. So how does this look?
Todd, excuse
Yep.
me. I've been asked to just step in and quickly do poll 3. And
Sure.
so I'm going to go ahead and launch that. And the question for poll 3, poll 3 is, what is your primary wavelength in DUV, UV? And the possible choices are 160 to 219 nanometers, 220 to 299 nanometers, 300 to 380 nanometers. No application in this wavelength region. Give people a couple more seconds. Okay, I'm going to close that poll and I'm going to share the responses with you. And I'm going to hide the poll. And everybody should be back to Todd's presentation. Please let me know if you are not.
Okay, we will continue on with the 3D optical components then. So on this slide here, we see interferograms. At the top left is our Heraeus 3D material grades, and at the bottom is a conventional or as produced fused silica. Now, as mentioned before, if we look side on, not just in the functional direction, you'll notice that the 3D material is homogeneous even in the side on. Whereas your conventional or as produced is going to have layers from the deposition process. Now, as mentioned earlier, Heraeus has invented a unique process of material homogenization that washes out the steep refractive index gradients. In this process, the striae are removed from the material. Heraeus materials are radially symmetric, which leads to the defocus or power being your main contributor when it comes to the Zernike terms. But anyone who's an optical finisher knows that power is one of the easiest things to remove in a polishing process. So for 3D optics, what do we need to do? We need to think about our light path. Where is the light going? What elements are needed to go within there? Are there any elements where the light is being transmitted in multiple directions where we need to make sure that we're preserving our wavefront? Be aware that the 3D materials, that there are claims for 3D material out there, but the Heraeus fused silica and quartz that has gone through our 3D homogenization process is the only real true 3D material. And of course, choose the 3D material when it comes to making these 3D optical components. So if we go to our spec sheet here, we're looking not only at the dark blue, but the light blue as well, which is our fused quartz. If we look at the numbers, anything that ends in a 2 is going to be a 2D material, or what we'd say is a material that's been homogenized in the functional direction. Anything that you see that has a 1 is actually one of our 3D materials. So you can see we have several different varieties of this. And then just to make things extra clear, if you see a cube on here or a box, a 3D cube, that means that this is a 3D material. So what have we learned? What do we need to specify? As far as geometries, we really want to consider your length, width, diameter, thickness, etc. Are you needing raw form material like an ingot? Do you need it as cut? Are you looking for a blank that's been ground or polished? What's the clear aperture you're thinking about? Always include tolerances. Do you need chamfers, etc.? All of these things are spelled out in the DIN ISO 10110. Additionally, you want to consider the application. What is the optical element? Is it a lens? Is it an A-sphere? Is it a debris shield? Consider what wavelength you're working at. Consider your lab conditions. If it's standard temperature and pressure, okay, this is going to be fine on most materials. But if it's a window for a vacuum chamber where you've got atmosphere on one side and 10 to the -8 torr on the other side, you're going to want to consider the stress that's placed on that window. Consider the light source, and then of course stress induced by refringence, homogeneity, bubbles, etc. Here's a drawing for just a random part, and what you can see on this is not only are the geometries called out, but they have their tolerances as well. There is a call out for the type of polish on the different surfaces, etc. But what's most important for this talk and most important for us is that I stay on the slide, is that the material spec is called out. And when we say the material spec is called out, it actually has a brand name, in this case Heraeus, and it has the grade, the supersil. And we know that it's the supersil, which is supersils are all the synthetic fused silica. This is a 3002. The 2 indicates that this is homogenized in the functional direction. If you just put fused silica on there, there's no telling what is actually going to be purchased or delivered. So try to be as specific as you can. The best analogy I would have is if you put on a spec sheet, I want a car. Well, you could either get a Ferrari or a Ford. You need to specify which material you're looking to get. So selecting is still challenging, right? And I know that we promised to solve some problems, so I want to show what we would propose to help you out. So this is our selection tool. As you can see, we have all of our various grades on here, including our high purity synthetic fused silicas, as well as the fused quartz products. And you can see that for these grades that there are multiple grades that would work for different specific, or for multiple wavelengths, I should say. The decision really depends on the application and some of the further optical properties. If you're in doubt on these, certainly give us a call. The way that this would work is that on our x-axis, we of course have our light spectrum, UV, vis, and near infrared, and on the y, we have the degree of homogenization. One thing that should be noted is that in the visible, any grade is going to work, but it doesn't make sense to specify a high-end, high-grade UV material such as Supercell 1 for a visible application. This would be a case of over-speccing, so spending a bit more money on something that you don't need. Now, you can't really infer cost based on the wavelength, so the x-axis doesn't tell you much about your cost factor, but the y-axis does, because each homogenization step is going to add an additional process, which does add additional cost. So if you only need a 2D material, don't spec a 3D material. Likewise, if you're putting a retroreflector, a prism, a very steep A-sphere, and etc., you're going to want to spec a 3D material, not an as-produced material. So I hope that this clears up a little bit of it. If we consider the spectrum in general, for the UV, your material choice is really going to depend on the UV radiation hardness that you need and the laser parameters, right? The wavelength, pulse duration, repetition rate, etc. And then on the other side of the spectrum, on the near infrared, the material choice is going to depend on what's acceptable for absorption, right? How much OH content can you have? What level of metallic impurities can you have? This is going to determine whether you'll go with a fused quartz or a fused silica, and whether you're going to go with a Supercell 311 that has OH content less than 300 ppm, or you're going to go for a 3001 that has the OH content of less than 1 ppm. And of course, consider the laser parameters. So that brings us to the conclusion here. There are a couple more slides that will pop up. Thank you all very much for your attention today, registering for this. As mentioned by Robin, this has all been recorded, so you can review that or share it, and the PDF is something that can be downloaded and distributed. Here is our web page. And at this point, we're going to go over to the questions that have been submitted and answer those. And for that, I'm seeking the assistance of Dr. Frank Nürnberg in Hanau, Germany. So he'll be coming in as well.
Thank you very much, Todd. And attendees, if you have questions, please add them now into the question box, and Dr. Jaeger and Dr. Nürnberg will be responding to your questions. So we have several questions here, and I will go ahead and begin with the first question we have. The maximum pressure it can tolerate is the question, and I think it is, what is the maximum pressure it can tolerate?
So good afternoon, my name is Frank Nürnberg, and I would like to answer all your questions you have. So regarding the maximum pressure of mostly common application here are pressure windows, depends on several parameters. It's of course the surface quality, it is the mounting, and the combination of pressure and thickness. So there is a theoretical equation which allows to calculate a maximum pressure for a certain thickness or vice versa, having a thickness to calculate the pressure. And this is a theoretical equation, and this is not containing the lab conditions, and that's very difficult for a material supplier to have more knowledge on the lab conditions. Therefore, certain safety factors are included, but it is really needed to have a live test on site. It can be calculated theoretically, but we would recommend to do really a live test here.
Okay, thank you. Next question. Can you comment on the AR coating and its potential impact on thermal lensing, even with a low OH fused silica?
So currently, this is the most discussed topic in laser applications. So it is all about absorption because the laser intensities and energies are increasing tremendously. So what we provide as Heraeus, we provide a material with the lowest absorption in the infrared, which is the wavelength range where the question is for. Of course, when you have a material with the lowest OH content, the lowest absorption, there's also a coating required, which has very low absorption. Otherwise, it wouldn't make sense to choose that material. If this is not the case, and we have a high absorption coating, for example, then the coating is has a certain temperature to a level that this temperature, as a heat dissipation moves into the fused silica material, is increasing the temperature of the fused silica material, means also the refractive index can change because there's a temperature dependency. And this might have an influence on focus shift. We see currently that for this sensitive applications where high laser energies are used, the low OH synthetic fused silica materials are the material of choice.
Okay, thank you. Next question here is, a customer asks about fluorescence in supersil. The rest of the question. I'm sorry. Is there, a customer asks about fluorescence in supersil. Is there a quantifiable statement possible?
We have here at Heraeus Quarzglas several spectrometers to be able to measure fluorescence over a wide wavelength range. Even excitation wavelengths resolved. So with that measurement possibility, we are able to give real numbers. The fluorescence, of course, depends on metallic impurities. So the natural fused quartz grades have, of course, higher fluorescence compared to the synthetic fused silica. You will find in our brochure here a dedicated column where with a simple test, certain fluorescence are described. If you have a special wavelength, please contact us after the presentation. We can give you support here.
Okay, thank you. And our next question here is there a common metrology for 3D homogeneity checking?
So the optical homogeneity is measured via interferometry. That means we are measuring in one dimension along the thickness of a material. And to resolve here the optical, the differences in the refractive index, of course, this is averaged along the thickness. And we can do that measurement in all 3 dimensions. So it is possible here to measure really a 3D material.
Okay, thank you very much. And our next question here is, can you tell me again for what applications are, as you called, 3D materials and suitable, what for applications 2D materials? So what applications are suitable for 3D materials and what for 2D materials?
So in principle, it is just ray tracing. If you have a window, you're looking straight through the thickness of an optic. Then it is important that you have the material homogenized in that one direction. And this is for all materials, as Todd already mentioned, with a 2 at the end. Typical applications are windows, thin debris shields, are lenses with a big radius. So that means a long focal length, because in that case, the deviation of the ray tracing in the material is small compared to the typical transmission direction, which is in functional direction. When you go to 3D application, here typically retroreflectors are used. Retroreflectors are optical components in which the ray tracing is in all 3 dimensions of the material. You use it as typical prisms, 90-degree prisms, for example. And we have seen issues here as well when you have lenses with a very short radius. That means a very strong curvature, and therefore the light is going also in more than just one direction through your material. These are typical applications where you differentiate between 3D and 2D material.
Okay, thank you very much. And here's our next question. Is there any correlation between homogeneity and birefringence?
So what we have seen in our material is when in the early stages of the production chain, if we try to measure the optical homogeneity, it's not possible to measure it due to the fact that the stress in the material is too high to resolve that. After our annealing steps, we are able to measure the optical homogeneity, and additional annealing processes enables us to reduce the stress which is in the material, which, for example, comes after the raw material production, so during the mechanical treatment of the material. This increases stress as well, and during an additional annealing process afterwards, we are reducing exactly this stress, and what we can see as well is that the optical homogeneity is reduced. However, the optical homogeneity in the material is more guided by the chemical composition and the distribution of the chemical impurities in the material, and the stress-induced birefringence is more influenced on the geometry itself, on sharp edges, and on mechanical treatment outside. So there is a small correlation possible, but not 100%.
Okay, thank you very much. And it looks like we have time for one last question here. And the question is, after listening to your presentation, I still wonder how I can determine the best price for the material I need.
So in general, what we told is that it is not so easy to give here a clear answer, because it depends on the parameters. It is not simple to have a rule here to determine the price by yourself. It's the geometry, it's the surface condition, it's the quality of the material, it's the volume. To be able to give here a precise answer, please contact our global sales officers and you get here your individual quote.
Okay, I thank you very much. And that is all the time we have for questions. At this time, I'm going to close the webinar, and a PDF of this presentation will be emailed to everybody who registered for this webinar, so you will be receiving a PDF of this presentation. A recording of this webinar will be available shortly, and you will receive a link to the recording tomorrow in a follow-up note. I would like to thank our presenter, Dr. Todd Jaeger, and Dr. Frank Nurnberg, and all of you for participating in today's webinar presented by Heraeus and hosted by Photonics Media.